Hello, let's solve problem number 3680, which is named General Schedule. So we've got n teams, and we got to generate a schedule such that every team plays every other team exactly twice, once at home, once away, and the hard thing is that there's one match per day and no team is allowed to play on consecutive days. Every team needs to have one rest day. And so the goal is to generate one of those valid schedules. And you can have many solutions. We don't care as long as it's correct. For n equals 2, you only have two teams. So you have to generate 0, 1 and 1, 0. So the match that's at home for team 0 and then the match that's at home for team 1. The problem is you can't have a day without any matches in between because there's no other teams and you're not allowed to have days without matches, right? So it's impossible. That's impossible, and that's why for n equals 2 return just an empty list. For n equals 3, it'll be the same problem. You have to, for example, you pick team 0 and 1 on day 1, and then on day 2 you have to pick two teams, but they can't be team 0 and they can't be team 1. So you have to pick team 2 and another one, but you're not allowed to pick 0, you're not allowed to pick 1. So again, impossible. And the same reasoning would apply if you had chosen 0 and 2 for the first team. Then for day 2, then you choose 1, and then you have to choose 0 or 2, but both have played on the first days. And for n equals 4, you can, for example, pick team 0 and 1 on day 1. Then on day 2, you have to pick 1 and 2 because those are the only two teams that weren't picked on day 1. And then on day 3, you have to pick again team 0 and 1. So you will do the opposite match. And then because there's 1 and 0 here, you have to pick 1 and 2 for day 4. And now you can see that we are just going to alternate between matches between team 0 and 1 and matches between team 1 and 2, right? There is no way I can ever have a match between team 0 and 2 because on those days I will necessarily have team 0 and 1, and on those days I will necessarily have team 1 and 2, right? So I'm stuck, and again, it's impossible. Basically, because there's only 4 teams, I pick 2 teams, then the day after necessarily the other 2, then the day after necessarily the first 2, then the day after necessarily the next 2, and then you can never mix those two clusters of 2 teams, basically. So this is a first sort of intuition. If n is smaller than 4, it's just not possible to generate a valid schedule. Now we have to find a way to generalize this for all n up to 50, and we will show and prove that if n is bigger or equal than 5, then it's always possible. And we're going to prove it's possible by just building a schedule such that it's possible. So to understand how we can build a valid schedule when n is bigger than 5, I'll just start by hopefully giving you an intuition of how we can come up with one of the many ways we can construct such schedules. Right, so let's take n equals 5. So we have the teams are team 0, 1, 2, 3, 4, 5. Sorry, 0, 1, 2, 3, 4. And how many matches do we need to generate? Well, we need to generate n times n minus 1 matches. The reason why is I need to generate all arrays of size 2 such that A is different than B. So for A, I have n choices. For B, I have n minus 1 choices because I can't choose B. So that's n times n minus 1 in total. Right, so 5 times 4 is 20 in this case. And one natural way of doing this would be to generate all matches where the teams are separated by 1, sort of a step size of 1. So let me explain what I mean. 0, 1, and then I can't do 1, 2, right? Because I can't repeat the 1. So I'm just going to jump to 2, 3, and then 4, 0, and then 1, 2, and then 3, 4, and then I stop. So what did I do? I did 0, 1, then I jumped to 2, 2, 3, and I jumped here. Because there's nothing here, I'm just cycling back to the beginning, so 4, 0. And after 4, 0, I have 1, 2, and after 1, 2, I have 3, 4. And after 3, 4, I would have 0, 1, but I already had 0, 1 initially. So I'll stop here. So the step size of 1 I'm referring here is just like the difference between the two teams' number. And I think that's a sort of valid way of generating a few valid matches. Obviously, if you do step size of 1 to generate those matches, you have to do 0, 1, and then 2, 3. You can't do 1, 2, right? Because you can't have team 1 playing twice in a row. Let's see what would happen if we were to generate the matches where the teams are separated by a sort of step size, quote unquote, of 2. So that would be 0, 2. And in the first example, I did 0, 1, and then the first team went from 0 to 2, and I did 2, 3. Then here, if I do this, I'll do 0, 2, and then 2, 4. But 2 would appear twice. But here I can just do 0, 2, 1, 3. So here the step size will be of 2, but the index here will have its own step size of, it used to have a step size of 2 here, and here it will have a sort of step size of 1. So you can see there's like sort of 2 different step sizes that we're talking about. So if I follow the logic, 0, 2, 1, 3, 2, 4, 3, 0, and 4, 1, and if I was to continue, I would have 0, 2 again. So there's a step size of 2 in the difference between the teams, but there's a step size of, I'll call this step size 2 of 1 if we look at by how much I shift myself when I generate those matches. And here we have this second step size 2 of 2. And I have to be clever when I choose them, but we'll see that it's not actually that hard. So if I keep going with a step size of 3, I'll generate, so let me maybe erase this. I'll have 0, 3, 1, 4, 2, 0, etc. So 0, 3, 1, 4, 2, 0, 3, 1, 4, 2, and then if I was to continue, I would go back to 0, 3, so I stop. And so here, again, the step size here is 3, but my sort of second step size, which I'm calling step size 2, is 1. And so to choose this one, I just have to be careful that I don't have any overlap. Initially, when the main step size was 1, I couldn't just have a step size 2 of 1 because 1 would appear twice. But for the rest, for now, everything's fine. And then we could continue with step size of 4. To get our 5 final matches. Step size equals 4. That would be 0, 4, 1, 0, 2, 1, 3, 2, 4, 3. Again, my second step size here can be 1 because I'm not overlapping. But this is something I should be careful in my code, right? It's sometimes not as straightforward. And actually, this is definitely not that straightforward, because here it doesn't work. If I choose step size 2 of 1, I have a 0 that repeats itself, I have the 1 that repeats itself as well. So as you can see, it's not that straightforward. For now, we'll just assume we can be clever. So a step size 2 of 1 here doesn't work, so let's try step size 2 of 2. So 0, 4, and then 2, 1, and then 4, 3, and then 1, 0, and then 3, 2, and then if I was to continue, I would go back to 0, 4. So I'm stopping here, and here the sort of optimal, I guess, step size is 1. Oh, it's 2. Step size 2 is 2. All right, so this choice here has to be smart enough so that I don't have collisions between day k and day k plus 1. I hope this is clear as a first intuition about how we could construct the global schedule. Second problem we could have is, now I probably would want to concatenate all of these matches in one single big array. But I have to be careful that none of the teams here overlap with the teams here, which is okay here, which is okay here, but here I have an overlap. And so I have a very easy way of fixing this, which would be just to pick this one as a starting point. And so sort of cyclically change this subarray by starting with 1, 0, and then bringing this one here, and this one here. And then I wouldn't have any worries, any problem. And because I've chosen step size 2 such that 2 consecutive, well, I haven't formally proven that we can, but if we admit that we can, because I've chosen step size 2 such that 2 matches here don't have any overlapping teams, and because the next logical one for this one was this one, I won't have any overlap here between 3, 2, and 0, 4. So now it seems, at least, that the only challenge is to choose step size 2 equals the right value in a smart fashion. There's actually a second challenge, which I think would be nicely highlighted if I pick n equals 6. So 0, 1, 2, 3, 4, 5 are the teams. And if I choose step size of 3, then I'll generate 0, 3, 1, 4, 2, 5. So that's just assuming I'm choosing step size 2 of 1, which seems to be working here. 0, 3, 1, 4, 2, 5, and then 3, 0, 4, 1, 5, 2, and then 0, 3 again. So I stop here. I guess this is fine. Well, I guess this is always fine. The problem I wanted to talk about was, if step size was 3 and step size 2 was 2, then I would have 0, 3, 2, 5, 4, 1, and then 0, 3 again. Right? Because 0, 3, 2, 5, 4, 1, and then plus 2, I'll be back here. But I have never generated 1, 4. even though it's got a step size of 3, right? So that's a problem. And that's just generally a problem if you've done other exercises of the same type. Whenever you have this step size 2, which is not co-prime with this number, then we have issues, I think. I'll give some other example. Is if n equals 10, 0, 1, up to 10, if step size 2 is 5, so no matter step size 1, then you would have 0. Actually, if n equals 10, this only goes up to 9, sorry. Then the next one would be 5, and the next one would be 10, but there's not in 10, so it goes back to 0. So you would just alternate between 0, 5, 0, 5, 0, 5, right? Just because this divides this. So we have to be careful. And you know, in this case, the easy solution is whenever you come back to 0, then you do 1, 6, and then you come back to 1. So then you do 2, 7, and then you come back to 2. Then you do 3, 8, then you come back to 3, so you go to the next one. 4, 9, you come back to 4, so you stop, and you go to the next one. The next one is 5, but you've had 5 already, so you stop. So this one is ignored. So that's the usual way we deal with this problem. Hopefully that was clear enough. If you've seen it before, it'll be very easy. If you haven't seen it before, when you'll see the code, it should be easy. The last challenge that we have is how to choose this step size 2. All right, so let me maybe be abstract here for a second, but if we have here step size, maybe we have, and then we have, this would be step size 2, and this would be step size as well. So just to clarify, if I put names A, B, C, D, first day I do AC, and second day I do BD, right? And so between A and B there's step size 2, that was the definition. Between B and D there's step size, and between A and C there's step size as well. That was again the definition of step size. And my worry is I do not want B, I don't want B to be equal to C. I also don't want D to be equal to A, because again, we're considering arrays and indices in everything mod the size of, not the size of the array, the number of teams, right? So I wouldn't want that D is actually A or C or whatever. So how do I ensure that B is not C? Well, I just want step size to be different than step size 2. How do I ensure that D is not the same as A? Well, I want that step size 2 plus step size different than n, right? Because if those are separated by n, because I'm considering everything mod n, then D would be A. I obviously also don't want B to be D, and I obviously don't want A to be C, but those are given because obviously step size is never 0. Right, so I don't need to worry about those. And I believe if B is different than C, C is different than A different than D, and D different than B, I think everything's different. So that's enough. So that's how I'll just choose step size 2, just such that those two conditions hold. And I only have two conditions, so they'll only take out two possibilities for step size 2, but I have n minus 1 possibilities for step size 2, anything between n and 1 and n minus 1, because obviously I can't have n. And n is at least 5, right? Because we said for n smaller or equal than 4, it doesn't work. So among those n minus 1 values, I have 2 that I'm forbidden to use, which is fine. I've got plenty of values. So that's how I'll make this work. And how can I ensure that I'll find some rearrangement of this such that there's no collision? And the answer is I have in there n matches and a collision, and I want this match and this match to have no overlapping team. But there's only 4 teams involved in those 2 matches, and n is at least 5, and there's no duplicate matches here. So that basically means it'll be easy for me to find a match such that those 4 teams don't overlap. I guess the formal argument would be that among those n matches, I want to find a match that doesn't have this or this. And there's only 2 matches that involve this minus and this plus. And there's only 2 matches that involve this. Again, this plus, and this minus. So there's 4 matches that involve these, and I have at least 5 matches. So that's the real argument. Sorry, that was nonsense. Cool. Whilst coding, I'll try to reiterate those arguments, but hopefully that should give you an overview of how we can solve this problem. Cool. So let's code this up. So for step size, I'll call this step size 1 in range 1 to n. I'm going to look for step size 2. Initially, I'll just initialize step size 2 to -1, and we said that the only 2 conditions I needed to check were these 2, and I have n minus 1 choices. So that shouldn't be too complicated. For step in range 1 to n, if step is not step size 1, which was our first condition, and step plus steps wise 1 different than n, which was our second condition, step plus step size 1 different than n, then I found a good step, so I can just break and say step size 2 equals step, and I can break. And just to make sure I always break, I could add an else and raise a value error. But here we have n is at least 5, we have at least 4 choices, and those 2 conditions remove 2 values at most. So we're sure we're never going to end up here. Then we said that we wanted to do this thing, right? Because step size 2 could theoretically divide the number of teams. So we have to avoid the infamous 0, 5, 0, 5, 0 loop, right? So what we'll do is we'll do multiples of step size 2, so 0, 5, until we go back to the first one. And when we go back to the first one, instead of starting at 0, we start at 1. And then we do multiples, and then we start at 2, and then we do multiples, and then we start at 3, and then we do multiples, etc., etc. That's kind of sort of a standard thing. So if you haven't seen it, you should probably know how to do it, and if you've seen it, it'll be very easy. So the way we do it is we have a list of visited teams. We'll have loads of these cycles. So in my example, the first cycle will be 0, 5, the second 1, 6, and at the end we'll just sort of use all of them. This is why it's a list of lists. It would be something, for my example, it would be something like 0, 5, 1, 6. Maybe if n was 15, let's do n equals 15, step size 2 equals 5. Then my example would look like 0, 5, 10, 1, 6, 11, 2, 7, 12, etc. Hopefully that additional example helps you. And so for start index, or just start in range n, so 0, 1, etc. If not visited starts, because when I arrive at 5, I don't want to do 5, 10, 0, right? Because I already have it. So if it's been visited already, I don't need to do anything. I'll just initialize a temporary cycle. And while not visited starts, visited start equals true, I append start, and start plus equal step size 2, and obviously start equals start mod n, and then I add cycles.append cyc, my temporary cycle. Hopefully that makes sense. And in cycles I'll have all of the first matches, so I only have this column. So in the schedule I just have to add lists of size 2 with the first element of cycle and that element plus the step size 1. Right? Hopefully it's not confusing that we have 2 step sizes, but this is the way we have to construct these schedules. So we'll just iterate through those cycles, and we could be tempted to do 0, 5, 10, and then 1, 6, 11 directly, etc., etc. But the problem is we have to be careful because we don't want to necessarily start at 0 here. If we start at 0, 4, because the last one ended at 4, 2, it was a bit dangerous, right? So whenever we deal with a new step size 1, we need to remember who were the last 2 teams in the last step size. So last home, initially we'll just put them to -1. But we have to be careful that the first teams in this new step size aren't those teams here. And so we'll code this later, but let's just pretend we have a magic method that just returns where we have to start here. Right, so we'll just do something like start index int equals self.magic method to find start index. We'll give it our current cycle, last home, last away, just the number of teams, and step size 1. Step size 1. Just so that it knows everything, right? We need the step size because we need to be aware of those 2. And we only have this one in cycle. So this is just this plus step size 1 mod the number of teams. And then we go through our cycles. So 14 range length of cycle. I is cycle of start index plus t, because we start at start index and then we go to start index plus 1, start index plus 2, start index plus 3, etc. But we do have to do mod length cyc, right? Because if we start at 4, we want to do 4, 5, 6, 0, 1, 2, 3, right? And then j, which is the other team, will just be I plus step size 1, again mod n, obviously. And then we can just add to the schedule ij, and we can set last home to I, last away to j. And notice that in this example I was just saying that we don't want overlaps between the last one of step size 1, 3 and the first one of step size 1, 4. But because we have those sub-cycles 0, 5 and then 1, 6, or in this example is 0, 5, 10 and then 1, 6, 11 and then 2, 7, 12, we also have to be careful that nothing here overlaps with nothing here, or nothing here collapses with anything here. So this is why this start index has to happen for every cycle, and these have to be set for any sub-cycles. All right, so those are the little cycles in the big bunch of matches we do for fixed step size 1. And then we can just return schedule. All right, so everything is done except for this magic method. So we need to define it. Cyc, which is a list of integers, last home, which is an int, last away, which is an int, and which is an int, and step size 1, which is an int. And this just returns an int. And so returns an index in cyc such that there are no collisions with last home and last away. First of all, if last home equals -1, then obviously we can just return 0, right? We don't need to care about anything if this is the first match we are outputting. Now, what are the bad teams? Bad in the sense that we're not allowed to select them, right? So there's obviously last home, there's obviously last away, but there's also last home minus step size 1, because we are currently in the phase where we put teams separated by step size 1. So if I'm using this as a start index, the match will be between last home minus step size 1 and last home minus step size 1 plus step size 1, which is last home. So there will be an overlap. And similarly, last away minus step size 1. Just to clarify, if I pick last home minus step size 1, this team will play against last home minus step size 1 plus step size 1, which is last home, which is illegal. Cool. So that's the reason why we do this, and that's also the reason why we do this. Obviously have to add mods operators here, because that could be a negative number, and we're doing everything mod n anyway, the number of teams. And so we just iterate in our temporary cycle, in our sub cycle, and if the team is not if team is not in the list of teams we're not allowed to choose, we can just return the index, right? Because I want this method to return an index. And here again, we could do something like raise value error if this is never chosen. But as I said, there's only 4 bad teams, 4 things we're not allowed to take. And we know that at this point, n is at least 5, right? So that was the proof I admittedly struggled to do on the whiteboard, but hopefully it makes sense now. There's probably loads of typos. Let's see. Yeah, I'm trying to, I've never defined this final schedule. So that will be a list of integers, right? The inner list is just a list of size 2. Other typos. Oh no, all right. Then we can submit. And that works. All right, so about the complexity, this is big O of n, another big O of n, so we big O of n squared right now. Here, this is big O of n, we have a nested loop, but this is still big O of n overall, because every time we're here, we're setting visited to something that wasn't true to true. And we can do this at most n times, because this list is size n. Right, so this overall is big O of n. The pending is big O of n amortized, so it's okay. This is a list of size n at most, so no worries about that. And cycles is a list of sublists, but you have all the n teams appear once and exactly once in those sublists. So maybe it's n equals 15 and you have 5 times 3, or 3 times 5, or maybe n is 60 and you have 12 times 5, but basically those two loops end up being big O of n. So this is a big O of n squared algorithm. N is 50, so we could have gotten away with n cube anyway, but the sort of true complexity here is n squared. And this method is big O of, well, let's say big O of n in the worst case, but we're only calling it, sorry, no, it's the same, yeah, right, no, sorry, it's the same. We are iterating in psych. So this is the same complexity as this, and so the same argument goes, this is overall big O of n.